Hello dear students, this is Devansha from NG Institute of Engineering and Technology. Again we continue with the same subject which is called basic electrical engineering. Right? So in our previous session we have discussed about the Thevenin theorem. Right? So before we start our next theorem which is called Norton theorem, we need to understand the basic of network. Now this is the same slide that we have discussed in our last session during the Thevenin theorem. So we already discussed the Thevenin theorem. Our next topic is the Norton theorem. So in this particular part, we are going to cover total circuit theorems, Thevenin theorem, Norton theorem, and superposition theorem. So as per why we are learning these theorems, that we once we design the circuit, then we have to analyze the circuit. So once we analyze the circuit, then let's say there are more number of resistors are connected in a circuit along with the various kinds of voltage sources and current source, dependent and independent. So ultimately, for a particular resistance, if we want to find a voltage drop or a current is passing through that particular resistance, we can find using various ways, various methods. So those methods we define in terms of the circuit theorem. So first part, Thevenin theorem, we already discussed. Now in our today's session, we are going to discuss about Norton's theorem, right? So once we learn the circuit theorem, then we have to go for a circuit analysis. The two kinds of analysis we are going to learn with, one is called the nodal analysis, another one is called the mesh analysis. So first let's start with basics of the network, where the one particular network, or you can consider as a circuit, the different parts of the circuit. So what is the circuit itself? So a path through which the current flows or intend to flow is defined as a circuit. So current must follow the closed path. It's called the circuit. So you can see this is the example of the circuit here. After that, we need to understand what is the node. So node or junction is nothing but a point where two or more elements are connected together is called as a node. So in another sense, you can also consider as a point where three or more than three branches are connected. At that particular point, we define as a node, right? Here, so you can see here there is a node at the point where three resistances are connected, R1, R2, and R3. So there are three branches are connected. Now, what do you mean the circuit branch? Where a part of the circuit or a network which lies between nodes or junction points, right? So ultimately, you can define here. These are the branch where there are three branches, maybe more branches, and each and every branch must consider a single element at least, as well as if you are going to connect more elements, all those elements must be in a series combination, right? Next part is called the loop, right? So a closed path in a circuit or a network is defined as a closed path, right? So for a circuit, closed path is must, or you can consider this is called a mesh, right? So these are the basics of network. You need to understand why this all the words somehow you're going to utilize in your theorem, right? So first we'll start with the Norton theorem. So it's nothing but the dual of Thevenin theorem. So if you know the Thevenin theorem, you can be able to understand the Norton theorem. Now, what is the statement? So any linear, bilinear, or active network with two output terminals can be replaced by the current source, which is called a short circuit current source (ISC), in parallel with a single equivalent resistance between these terminals A and B, as shown in figure. So you can see here. In this particular figure, there is a given network is there, where there are two terminals A and B, where RF is connected. So you have to reduce the big given network or linear or active network into a one current source, which is called ISC, in parallel with the equivalent resistance, right? So both are in parallel, and then you have to connect your actual R, right? So here the ISC is nothing but the Norton equivalent current source, where if you remove the RL at the initial part, then you have to make it that particular terminal A and B are short, and whatever current which is passing through terminal A and B, that is defined as defined is your short circuit current, right? Same way, RM is called the Norton equivalent resistance. Now this is the same resistance and same using the same method that what we have used in a Thevenin theorem. By that way, you can also find the Thevenin equivalent resistance, or it is also defined as the Norton equivalent resistance, right? Now here you can see here the complete active network is converted into a two component. One is called ISC, another one is called RN, and both are in a parallel. Then you can connect your load resistance where actual current which is passing through RL, that current is IL, right? So here there are there are four steps to solve this network here. So my first step is always like remove the RL first, and then between terminal A and B, and make that terminal A and B short, right? So by that way, whatever current which is passing through this terminal A and B, that is defined as the short circuit current, ISC. My next job is to find ISC. Then using KVL, KCL, voltage divider, current divider. Step number 3, that again I have to find the resistance RN, or you can consider as a RTH, by making all voltage sources short and all current sources open, right? Then step number 4, I have to find the IL current passing through resistor RL. So that IL you can find using a current divider rule. So here the equation you have to follow is IL, right? So if you can see our previous design where you can find the value of IL using the current divider rule, that is equal to the opposite direction of resistance, which is Rn, divided by Rn plus RL into the total flowing current, which is called ISC. So here again I am going to repeat the equation of IL is equal to Rn divided by Rn plus RL into ISC, right? By that way you can find the load current. Now let's define one example. So this is what the actual circuit, that is R1, R2, R3 is given, RL is also given, that's between terminal A and B. So what I have to do, I have to use my first step, that's what discuss that matter, which is step number 1, and remove the RL and short the current A and B, then find out ISC. And then how you can find the ISC is just find the total resistance of the network. So for this particular circuit you can find your total resistance RT is equal to R1 plus the parallel combination of R2 and R3, right? Then you have to find the circuit current I, that is equal to E by R, and from then you can find ISC is equal to I into R2 divided by R2 plus R3. Then you can see the second network from here. Next part, when you have to use the step number 3, where your next job is to find the equivalent resistance. You can consider as a Rn or RTH, where you can find from this network as Rn is nothing but R1 parallel R2 plus R3. So here you have to look from the terminal A and B. Here you have to look from the terminal A and B, and then you can see here R1 and R2 both are in parallel in series with the R3, right? So that would be your equivalent resistance. You can check here. And then you have to finally find the current which is passing through the load resistor RL. So that you can see here from this ISC RL, and then you can connect your RL, that is here IL is passing through the RL. So the IL is nothing but ISC into RN divided by RN plus RL. That part we have already discussed. So this is what the different steps to find or to analyze any circuit using the Norton theorem. Now let's say one of the example where you have applied 120 volt and there are three resistances are connected, 10 ohm, 10 ohm and 5 ohm, and one more resistance which is connected between terminal A and B is a 5 ohm, that you consider yours RL, that's a load resistor, right? So my next job is to find the current which is passing through terminal A and B, that current I define as a short circuit current, which is called a ISC, right? So here you can define this current as ISC current. So my first part is the remove the RL and short the terminal A and B. From that you can find the ISC, which is short circuit current. Before that you have to find the total resistance of the network. So once you look from 120 volt supply, then here 10 and 5 volt, 10 ohm and 5 ohm, these two resistances are in parallel with the 10 ohm resistance in series. So by that way you can be able to find 13.33 ohm, which is your total resistance of the circuit. From there you can find the current, the total current of the circuit, which is passing through 10 ohm resistance, that is 9 ampere, and from that you can be able to find the ISC using current divider rule. you use this equation like I is equal to 9 ampere, so 9 multiplied by 10 divided by 10 plus 15. Using the current divider rule, you can find the value of ISC, right? So that is 6 ampere. Now ISC is 6 ampere. My next job is to find the equivalent resistance RN. That RN you can find by making all voltage sources short and all current sources open. So in this particular network, you have to make it 120 volt short, right? So once you make the 120 volt short here, right? That means you have to look from terminal A and B, and that's your equivalent resistance R, right? So from here you can see that 10 ohm and 10 ohm resistance are in parallel with 5 ohm resistance in series. So from that you can be able to find RN, that value is 5 ohm, and finally you have to connect RL between terminal A and B, and you have to find the load current IL which is passing through RL. So by this equation, IL is equal to ISC RN divided by RN plus RL. The same equation, you put the value, then you can find 4 ampere. So this is one of the example based on all these 4 steps. Again, we are going to repeat the same example that we have discussed during the Thevenin theorem. You can see this, where there are two voltage sources, 10 volt, 20 volt, 3 resistances, 10, 10 and 40 ohm, where again you have to remove the RL and you have to make A and B short. So you can make A and B short, and through A and B, whatever current which is passing through, that current is ISC current. So my next job is to find ISC current. So if I am looking for my ISC current, I have to find total circuit resistance, then total circuit current. From that, I can be able to find ISC by using the current divider rule. So quickly we can see here, you can find, see here, we have used one of the important theorem, that is called the source transformation theorem. Not the complete theorem, but we just use the equation. That is called the source transformation. So what I have done here, from 10 ohm to 10 ohm, 10 volt to 10 ohm, and here you can see here 20 volt to 10 ohm. These two are the voltage source. So one voltage source in series with the resistance I have converted into a current source. So voltage divided by resistance, that you can find the current, and that current is called the ohms, based on the ohms law. So that I is equal to V by R. So I find 10 divided by 10 is the 1 ampere current. So you can see this this particular circuit where 1 ampere current is there, and whatever resistance in series here, you just find the current source. So that 10 volt divided by 10 ohm, so that's a 1 ampere current. Again same here, 20 volt divided by 10 is a 2 ampere current. So ultimately these two currents are passing through 10 ohm and 10 ohm, right? So you can also utilize this, you can simplify this network by that way, or you can also use some voltage divider method, you can find, or current divider method, and you can find ISC. So by this way you can also find the total ISC, that would be 1 ampere current and 2 ampere current. These two are ultimately meeting at the terminal A and B, right? So my ISC current would be 1 ampere plus 2 ampere, so that would be a 3 ampere. So from this I can be able to find the equivalent resistance, which is called Rn. To make these two voltage sources, you have to make it a short. So ultimately voltage source becomes 0. So here from Rn, from this particular network, you can see Rn is looking for terminal A and B, where two resistances 10 ohm and 10 ohm both are in a parallel with each other. So from this Rn is parallel, a combination of 10 and 10, you can find the value of 5 ohm. So ultimately the Norton equivalent you can see here, 3 ampere ISC, then Rn is 5, and now I have to connect the RL, that is called the 40 ohm, right? So from this you can straight away see, this is the current source, that is a part of the Norton theorem, that using the source transformation you can convert into a voltage source. So that the next equivalent circuitry we define the Thevenin theorem, right? So here you can either use current divider rule, or straight away you can find the value of IL, that is equal to 15 divided by 5 plus 40 using the Thevenin. That is also possible, but since it is a simplified network, so you can either both the equation. You can use either equation. You can find the value of IN, which is IN or IL, which is nothing but 0.33 ampere, which is the current passing through the 40 ohm resistance, right? So the most important part is here how you can relate both Norton and Thevenin. So ultimately Thevenin theorem says that any network can be represented or can be converted into a voltage source and in series resistance. Right? Same way, Norton says the same thing, but in terms of the current source. So any network in a Norton theorem says the same network can be represented by a current and in shunt with the resistance. Right? So ultimately, this shows the source transformation of Thevenin theorem. It becomes the Norton theorem. Simple, right? So that terminology we define as a source transformation. There's a simply both the way conversion is possible. You can see from this. This is also a best example of the source transformation where 15 volt voltage source is there in series with the 3 ohm resistance. So this is defined as a voltage source. Now I need to convert this voltage source into current source. So 15 divided by 3. So it's a 5 ampere current source which is in opposite up direction, because the 15 volt is a plus and minus here in the first circuit. Same with 3 ohm resistance in series with the voltage source. That the same 3 volt resistance you have to connect in a parallel with the current source, right? So that's called the source transformation. So ultimately here Nortons is nothing but the source transformation of Thevenin and vice versa. So Thevenin is more related to the voltage source and Norton is more related with the current source. Okay. So thank you very much, dear students. If you have any question, you can write in the comment box. Thank you very much.